Welcome to Advanced Group Theory. Today, we are going to explore one of the most powerful and fascinating concepts in abstract algebra, known as Sylow p-Subgroups. If you have ever wondered how mathematicians break down massive, complex symmetrical structures into manageable pieces, you are in the right place. We will build this understanding from the ground up, so let us dive right in. Now that we are ready to begin, let us imagine a massive global corporation with thousands of employees. Think of the entire corporation as a mathematical group and the employees as the individual elements inside it. Suppose we want to form a special task force where every single member must possess a specific rare skill, like speaking fluent Japanese. We can call this specific skill our prime number, P. A team where everyone has this skill is called a P group. A Sylow p-Subgroup is simply the absolute largest Japanese-speaking task force you can possibly assemble from the company roster. If you try to add even one more person, they will not speak the language. It is the biggest possible chunk of a group built entirely around one specific prime number. To understand this concept formally, we first need to look at the order of a group. Why does the order matter? Because the order of a group is simply the total number of elements or items contained inside it, and it dictates the group's entire structure. Let us call the main group G, and its total size is denoted by the absolute value symbol around G. According to the fundamental theorem of arithmetic, we can break this total size down into a multiplication of prime numbers, which is called prime factorization. Suppose we isolate one specific prime number p and find the absolute highest power of p that divides the total size of the group. This maximum prime power is exactly what we need to find our special subgroups. This brings us to the mathematical representation of our group size. Where does this formula come from? It is a direct application of prime factorization. We write the total order of the group G as p raised to the power of n multiplied by m. Let us break down every symbol. The absolute value of G is the total number of elements in our main group. The letter P stands for our chosen prime number and n is its highest exponent. The letter m represents all the leftover factors multiplied together. Crucially, the greatest common divisor of p and m must be exactly 1, meaning p does not divide m at all. If the variable n increases, the size of the prime-powered portion grows, leaving less for the remainder m. This equation perfectly separates our prime of interest from the rest of the group. Now that we have separated our prime and ensured no parts were left behind in the remainder, we can define the actual subgroup. This formula tells us the exact size of the special smaller group we are looking for. The capital letter P represents our Sylow p-Subgroup. The vertical bars around P denote its order, which simply means the number of elements inside it. The formula states that the size of this subgroup is exactly equal to the maximum prime power, p raised to n, that we found in the previous step. If the prime power increases, the size of this subgroup increases proportionally. This confirms that the subgroup P is as large as it can possibly be without mixing in any other prime factors. It is a pure, unmixed mathematical building block. Before we move on to a concrete example, let us visualize what this looks like. Here you are seeing a large outer circle labeled G. This represents our entire main group, containing all possible elements. Inside it, you will notice a smaller, solid blue circle labeled P. This is our Sylow p-Subgroup. Notice how it sits entirely within G, meaning it is a self-contained subgroup. Inside P, there are even smaller circles, which represent smaller subgroups of the same prime power. However, P is the outermost blue boundary. This visually reinforces our concept. The Sylow p-Subgroup is the absolute largest possible piece of the group whose size is a pure power of that specific prime. You cannot draw a larger blue circle without stepping outside the rules. Now that we have our formulas and a visual understanding, let us see this with a concrete example. We are given a generic group that contains exactly 12 elements, and we are asked to find the required sizes for its Sylow p-Subgroups. We do not need to know the exact identities of the elements, only the total order. Why do we use our factorization approach here? Because breaking the number 12 down into its prime building blocks will directly reveal the maximum prime powers. We start by writing the total size of the group, which is 12. We then factor 12 into prime numbers, resulting in 2 squared multiplied by 3 to the first power. This shows us that the group size is built from two distinct prime numbers, 2 and 3. Continuing with our factored group size, we will now isolate our first prime. We focus on the prime number 2, setting it as our first prime, P1. Looking at our factorization, the highest power attached to this prime is 2, which becomes our exponent, N1. The leftover portion of the factorization is simply 3, which becomes our remainder, M1. We must always check our condition. The greatest common divisor of 2 and 3 is exactly 1. This means they share no common factors, satisfying our mathematical requirements perfectly. We have successfully isolated the maximum power of 2 that exists inside the number 12, and we are now ready to calculate the size of the first Sylow subgroup. Let us finalize the sizes for both subgroups. For our first prime, 2, we calculate the size of the Sylow subgroup, denoted as P2. By raising our prime 2 to its maximum power of 2, we get 4. This means any Sylow 2 subgroup inside this group will contain exactly 4 elements. Next, we shift our attention to the second prime number, 3. The highest power attached to this prime is 1. Raising 3 to the power of 1 gives us exactly 3. Therefore, any Sylow 3 subgroup inside this group will contain exactly 3 elements. Physically, this means if you have a symmetrical system with 12 states, the largest pure subsystems you can isolate will have exactly 4 states and 3 states, respectively. Having found just the sizes in a generic group, let us look at a specific real-world mathematical group to find the actual elements. We are given the symmetric group of order 6, known as S3. This group consists of all the possible ways to shuffle or rearrange 3 distinct items. We are asked to find the actual elements that make up its Sylow subgroups. We choose our factorization approach again to find the target sizes first. The total number of ways to shuffle 3 items is 6. So the order of our group is 6. We factor 6 into its prime components, which are 2 and 3, both raised to the power of 1. This tells us exactly what sizes of subgroups we need to hunt for inside the shuffling operations. Continuing with our symmetric group, we first look for the Sylow 2 subgroup. From our factorization, we establish that the size of this subgroup must be exactly 2. Why does this matter? Because a subgroup of size 2 is very restricted. It must contain the do-nothing action, called the identity element, and exactly one other action that reverses itself. In the physical context of shuffling items, an action that reverses itself is a simple swap of 2 items. If you swap them twice, you are back where you started. We search the main group and find that there are 3 different simple swaps available. This means we can form multiple valid subgroups of this exact size. Let us write down our final subgroups. Here, we list the actual Sylow 2 subgroups found inside the main group. The symbol E represents the identity element, while numbers in parentheses represent swapping those specific items. Interestingly, we find 3 different subgroups that fit the criteria perfectly, which is completely normal in group theory. Next, we establish that the size of the Sylow 3 subgroup must be exactly 3. This requires the identity element and 2 actions that cycle through all 3 items. We identify the single Sylow 3 subgroup containing the forward and backward cycles. Unlike the previous case, there is only one unique subgroup of this size. Physically, this shows us the exact fundamental shuffling symmetries hidden inside the larger group. Now that we have successfully found these subgroups, you might wonder why mathematicians care so much about them. The reason is that they serve as the fundamental skeleton or the DNA of finite groups. If you want to understand a massive, complicated group, analyzing the whole thing at once is often completely impossible. Instead, you break it down into these prime powered chunks, which are much easier to study. In advanced fields like cryptography, quantum physics, and chemistry, understanding the symmetry of a system relies entirely on understanding these building blocks. Without Sylow subgroups, classifying the structure of the universe's symmetries would be an unsolvable puzzle. They are the key to unlocking complex mathematical systems. We have covered a lot of ground today, so let us summarize the most important ideas. First, remember that a Sylow p-subgroup is simply the largest possible piece of a group whose size is a pure power of a specific prime number. Second, we find its exact size by factoring the total number of elements in the main group and isolating the maximum power of that prime. Third, as we saw with the symmetric group, a single group can contain multiple Sylow subgroups for the same prime, as long as they are the same size. You have now mastered the fundamental building blocks of abstract algebra. Excellent work today, and keep exploring these beautiful mathematical structures.